And welcome back. Example 3 says find the sum of 1 over n times n plus 1. The first thing to note is that this is not geometric. Not a geometric series. It's not geometric, but we're going to be able to figure out what the series evaluates to in a little bit. But it's not geometric because it's not in the form ar to the n minus 1, and there's no way that you could put it in that form. The n's are not in the exponents, they're just down in the bottom of the fraction. Also, you're not really multiplying to get from one term to the next. If you wrote out these terms, you can realize that there's no way that this is a geometric series. You're not always multiplying by the same number to get to the next number. But the way we're going to figure this out is we're going to take the inside fraction and use partial fraction decomposition to break it up into two fractions that are subtracted. So I'm going to write this as a separate note, and you can verify this for yourself, that the original series can be rewritten as the series 1 over n minus 1 over n plus 1. And this, again, you can do by partial fractions. Partial fraction decomposition. Now, it turns out this new form of the terms are going to help us out quite a lot. We'll try to figure out what the nth partial sum looks like, and when we do, we're going to see that something magical happens. Let's write out the nth partial sum. So the first term of that nth partial sum there is going to be, well, n equals 1. So we're going to plug in n equals 1, and we're going to get 1 over 1 minus 1 over 1 plus 1, which is 2. The second one, we're going to plug in n equals 2, so that's 1 over 2 minus 1 over 2 plus 1, which is 3. Then we get 1 over 3 minus 1 over 4, and so on. The legs started itching. And there are going to be a bunch more terms, but eventually we can pick up the trail at the n minus first term. So that's the one that comes right before the last term is the n minus first term. That'll be 1 over n minus 1 minus 1 over n. Then we have plus the nth term, which will be 1 over n minus 1 over n plus 1. Okay. Now for the magic. Notice that the minus 1/2 and the plus 1/2, those ones are the same but just opposite signs. So those are going to cancel. Notice the minus 1/3 and the plus 1/3. Those are the same, but they just have the opposite signs. So those will cancel. Notice that you're going to have a minus 1/4 as the second term of inside this parenthesis, and then there's going to be a positive 1/4 as the first part of the next term. So there's going to be a minus 1/4 and a plus 1/4 that'll cancel here. And all the middle terms are going to cancel, right? There's going to be a 1 over n minus 1 term that's positive here, and a minus 1 over n term that's going to be negative right before it. So you'll have something canceling off this 1 over n minus 1 as well. The 1 over n, the negative 1 over n, and the positive 1 over n will cancel. Now there won't be anything to cancel off this negative 1 over n plus 1 because that would have to come from the next term. And there won't be anything to cancel off the 1 because that would have to come from the previous term, which there isn't any. So those are the only two things that are left. The whole rest of the partial sum degenerates into 1 minus 1 over n plus 1. So the whole partial sum collapses down into just 1 minus 1 over n plus 1. This kind of phenomenon that happens here, that collapsing down, is called a telescoping sum. So this is a telescoping sum. If you see like a telescope and you collapse it down, then it collapses down into something small. Or as a student corrected me one semester, it's not really exactly like a telescope. It's more like one of those spy glasses, like in the pirate days, right? Arr. The pirate theme runs strong in this section. So the spy glass, where you take it, you extend it out, and then you can look through it, and then you collapse it back, and you can stick it in your pocket. Great. So either the telescoping sums, or I guess you could call them the spyglass sums if you like. So here we have the nth partial sum can be written in this closed form now, 1 minus 1 over n plus 1. So with the geometric series, we had one method for getting the closed forms. For these telescoping sums kind of series, we have this other way of getting a closed form, which is just to write out all the terms and then notice the cancellation that happens. It all collapses down. So now we're going to take the limit of the partial sums. When we do this, the fraction will go to 0, so we'll just get 1 minus 0, which is 1. And thus, the series will do the same thing. It's going to approach 1 as well. So the series, as n goes from 1 to infinity, of 1 over n times n plus 1 will equal 1 as well. The series does whatever its partial sums do as n goes to infinity. So that's pretty cool. That's just a little technique for evaluating certain types of series. It's not going to handle all of them, and not even really most of them. It's just going to handle a select class of series. Okay. Something that's important to understand is that if a series converges, then the terms have to go to 0. So if a series converges, the terms of the series have to approach 0. As an example, because the series we figured out, 1 over n times n plus 1, that as a series converged, the terms have to go to 0. Now we could have just looked at the terms and said, well, of course they go to 0, because 1 over n times n plus 1, if you take the limit as n approaches infinity, the bottom blows up to infinity, so 1 over that is going to shrink down to 0. But this is just an example of that theorem. The more important theorem is going to come from the contrapositive of that, which says if the terms do not go to 0, so if the limit doesn't exist, or it does exist and just doesn't give you 0, then the series is going to diverge. So if the terms do not go to 0, so they approach some non-zero number, or the terms, the limit just does not exist, then the series, when you add up all those terms, diverges. Let's look at example 4 here. So we're given an example for the sum as n goes from 1 to infinity of n squared. So what we can write here is that the limit as n approaches infinity of n squared is infinity, right? As n goes to infinity, n squared goes to infinity. This is like a does not exist kind of case. Usually we were specific about our does not exist, and we would write infinity as the answer to the limit. So another way you could say this is this does not exist includes plus or minus infinity, and the regular does not exist, like the DNE. It's a little repetitive there, but just to give you the idea that this is any kind of divergence for a limit, or not existing of a limit. So in this case, the limit of the terms is not 0, and so the series diverges. The series n squared diverges. And I forgot to mention, this is called the test for divergence. Something else I forgot to mention is that this is also called the nth term test. In case you ever hear it referred to that, you'll know what it is. Test for divergence. We'll call it the test for divergence, but you can also call it the nth term test. Let's look at example 5. We have the series as n goes from 1 to infinity of n squared over 5n squared plus 4. Does that one converge or does it diverge? Well, let's take the limit of the terms and see if they go to 0. If they do, then it's possible it converges. If the terms do not go to 0, then the series diverges for sure. Now to evaluate this limit, we can divide the top and the bottom by n squared. That's the highest powered term, aside from its coefficient. So divide the top and the bottom by n squared, and we get 1 over 5 plus 0, which is 1/5. And because that's not 0, the test for divergence says that the series diverges. Again, by the test for divergence. One way you could interpret this here to get a sense of the intuition is that the limit of the terms is telling you what these terms are getting closer to as n goes to infinity. So when n is really large, these terms that we're adding up in the series are getting close to 1/5. So eventually it's like you're adding up a number that's really close to 1/5 plus a number that's really close to 1/5 plus another number that's getting close to 1/5. They're not exactly equal to 1/5, but they're super duper close to 1/5 as n gets really large. And when you just add up an infinite number of 1/5, that's going to blow up to infinity, right? If you keep adding 1/5 an infinite number of times, that's going to be blowing up to infinity. So because the terms do not go to 0, they go to some other number. When you add up those numbers an infinite number of times, that's going to diverge. So that's the intuition behind the test for divergence. But the terms don't have to go to a specific finite number that's non-zero. They could just keep oscillating back and forth, like in example 6. If we take a look at this series as n goes from 1 to infinity of -1 to the n plus 1, when we consider the terms of the series and take the limit as n approaches infinity of those terms, that limit does not exist because of the oscillation back and forth between 1, -1, 1, -1, 1, -1. We've looked at this limit before, and it does not exist. So the series diverges. If the terms don't go to 0, when you add them up, that series is going to diverge. Again, by the test for divergence. Okay, so a little caution here is that sometimes you might think, oh, well, as long as I can figure out if the terms go to 0, then the series will converge, right? But that's not always the case. Sometimes the terms are going to go to 0, so the limit as n approaches infinity of the terms of the series approach 0. So shrinking down to 0, so that's a good sign. But yet the series itself could diverge. So just because the terms go to 0, you don't really know if the series converges or if it diverges. Either one could happen. So here's an example of the terms going to 0 and yet the series diverging. 1 over n. If you take the limit as n approaches infinity of 1 over n, that equals 0. But the series 1 over n diverges. If you add up all those terms, it diverges. Let's show that. The way we're going to show that is by looking at the partial sums. And we're not going to look at the partial sums s sub 1, s sub 2, s sub 3, and s sub 4, and so on. We're going to look at s sub 2, s sub 4, s sub 8, s sub 16, and so on. So we're looking at the powers of 2 partial sums. So s sub 2 means the sum of the first 2 terms of this 1 over n series. That would be 1 plus 1/2. Right? Plug in n equals 1, and you get 1 over 1, which is 1. Then plug in n equals 2, and you get 1 over 2. Add those 2 terms up, and you've got the partial sum. The sum of the first 2 terms. Okay, I'm actually going to highlight this 1 over 2 in green. I'm actually going to highlight the 1 over 2 in red. Okay, just because. Keep your eye on the 1 over 2. All right, now s sub 4 is s sub 4 is going to be 1 plus 1/2 plus. Now we're going to write 1/3 plus 1/4. So that's the sum of the first 4 terms. Now what we're going to do is a little bit tricky. We're going to rewrite this so that we get a different kind of sum. We're going to write this as, whoops. We're going to write this as 1/4 plus 1/4. And we can do that because 1/3 is bigger than 1/4. So here, when we're moving from left to right, we're making a smaller summation, right? Because we're just taking one of those fractions and making it smaller. And the reason we're making it smaller to become 1/4 is because we can add these two together and get 1/2. Which then combines with the other half and gives you 1 plus 2 over 2. You could write 1 plus 1 equals 2, but I'm going to leave it like this. Keep your eye on the 1/2, the 2 over 2, and so on. Nothing up my sleeve, nothing up my sleeve. I have short sleeves. All right, well, let's look at s sub 8, the sum of the first 8. Sum of the first 8 terms. Okay, I need a color here for this. Let me use this one. 1/5 plus 1/6 plus 1/7 plus 1/8. There we go. Okay. So all of those ones, all of those s sub 8 terms, those are all, if you add them all up, greater than 1 plus 1/2 plus 1/4 plus 1/4. So we're still going to use the same trick on those two. So by getting that denominator of 1/4 the same, we were able to collapse these two into a half to combine with the other half here. We're going to do the same trick with these terms. We're going to write 1 over 8 for all of these. Now notice we had to have 4 more terms, right? This is why we're going to double the partial sum that we're looking at, so that because our denominator is going to double, and so we need 4 of these terms to make the top have a 4, and then 4/8 simplifies down to a half. So we're going to have 1 plus 1/2 plus 1/2 plus 1/2, which is 1 plus now 3 halves. Now the actual partial sum is even bigger than that, but notice what's happening here. The farther out we're going in the partial sums, we eventually get to 1 plus 1/2. Then later in the partial sums, we get to 1 plus 2 halves. Then later in the partial sums, we get to 1 plus 3 halves. Eventually, you can imagine we're going to get to 1 plus 4 halves and 1 plus 5 halves, 1 plus 6 halves, and so on. Let me actually write up a couple more of these here. So we have S sub 16 equals, through this same process, something that's greater than 1 plus 4 halves. And then S sub 32 will give you something that's greater than 1 plus 5 halves, and so on. So taking it down over here, we have S sub 2 to the n, right? These are powers of 2 that we're looking at, 2, 4, 8, 16, 32. S sub 2 to the power of n. Well, let's see, when we had 2, that's like 2 to the 1, and we had a 1 up here. When we have 4, that's 2 to the 2, and we had a 2 up here. 8 is 2 to the 3, and we had a 3 up here. So S sub 2 to the n is greater than 1 plus n to the 2. Sorry, n over 2. But that's going to approach infinity as n approaches infinity. So our partial sums of the 1 over n series are bigger than these expressions right here, which themselves are blowing up to infinity. So our partial sums are going to blow up to infinity as well. And so the partial sums as a sequence diverge. And so, that's a lot of so's, so. The series 1 over n diverges. So we've shown that the series 1 over n diverges. So that's pretty nice. Thanks so much for watching, and I'll see you in the next video.